My name is Max Pittner from Bosch and I will present our latest work called SparseLaneSTP, leveraging spatio-temporal priors with sparse transformers for 3D lane detection. Traditionally, monocular 3D lane detection has been tackled using a two-stage approach, where the first stage is to create a dense BEV feature representation via a learned transformation. In a second stage, an anchor-based detector uses these features to predict 3D lanes. Such methods suffer under specific drawbacks like a potentially misaligned BEV representations due to transformation errors that cannot be corrected in the detection stage. A far-range BEV representation also requires high computational cost and, lastly, the anchor-based architectures relies on specific heuristics. Recently, transformers in combination with the sparse query designs solved these issues and outperformed BEV approaches by modeling lanes as position-aware queries that are directly associated with the perspective view, avoiding an error-prone BEV. These queries are optimized using attention mechanisms in the transformer decoder in an iterative process. However, such sparse transformer approaches so far completely neglect valuable prior knowledge about lane-specific properties or temporal history. In SparseLaneSTP, we are proposing a transformer-based lane detector that leverages these spatio-temporal priors. We base our approach on a sparse transformer architecture similar to LATR as illustrated here. As proposed in our previous works like LaneCPP, we leverage the benefits of continuous representations. Therefore, we propose a spline-based line function tailored for this architecture and model spline control points as queries that are iteratively refined by the transformers. The hereby used Catmull-Ram spline is simply computed by this function, where its geometry and visibility is completely defined by the control point matrix P predicted by the network. While former methods used global self-attention to model relationships between all queries, our idea is to integrate lane-specific priors and temporal knowledge into the attention mechanism. Based on spatial properties of lanes, we formulate attention that enables the network to fully focus on the relevant query relations to capture the lane structure and to ignore redundant relations present in usual self-attention. Another source of prior knowledge lies in the history of observations. We leverage this knowledge by formulating a temporal cross-attention mechanism that allows information exchange of current queries with previous queries stored in a memory queue, allowing the network to resolve ambiguities and properly handle temporary occlusions. Finally, inspired by LaneCPP, we formulate auxiliary loss functions based on priors to regularize the lane representation. Besides spatial priors from LaneCPP, we also present a temporal regularization for more consistent detection behavior. We conduct several experiments on OpenLane as well as other datasets and show that each of our proposed contributions results in significant improvements. The most positive effect is caused by our main contribution, spatio-temporal attention. Combinations of spatial attention mechanisms SLA and PNA result in increased F-score, and adding temporal cross-attention proves best results. We also demonstrate the effect of using temporal knowledge in qualitative examples. Here we compare a non-temporal and a temporal model in the situation of a partial occlusion of a hardly visible line. While the non-temporal model loses the line in subsequent frames, the temporal model shows better consistency and maintains the prediction even though the occlusion gets worse. We compare our method to several baselines and show a quantitative comparison to the most prominent baselines on the OpenLane benchmark. SparseLaneSTP achieves superior performance in detection scores as well as geometric errors in near and far range. For the full comparison that includes other baselines and datasets, we refer to the paper. A qualitative comparison to our main baseline LATR showcases a more robust perception behavior of SparseLaneSTP for dynamic occlusions due to temporal modeling and succeeds in capturing hardly visible structures due to spatial priors. Our prior-based regularization enhances this behavior, for example by favoring parallel line structures in cases of hardly visible lines in the far range. Independent of our proposed model, we observe that current 3D lane datasets suffer under the fact that merely LiDAR skin points are used to recover the 3D information. This approach unfortunately often results in severe outliers and noise. We instead propose a simple yet efficient auto-labeling pipeline using temporal aggregation instead of relying on LiDAR, which is described in more detail in the paper. Consequently, we end up with noise-free and accurate 3D lane geometry, including visibility information up to a far range of more than 200 meters. We also provide first results of SparseLaneSTP on our novel 3D lane dataset and provide a quantitative comparison to baselines in the paper. We thank all listeners for their attention and encourage them to read our paper to learn more about our work.